What's up guys, welcome back. Today I wanted to do some exam style questions on annuities. I'm going to do a bunch of them. It's going to be quite a long video, but I wanted to give you a kind of experience on the type of questions they can ask in Standard 2 on annuities. I know it gives a lot of kids problems and a lot of students kind of get stuck, so hopefully by watching this video you'll kind of clear things up on how to approach questions and what type of strategies you can apply for yourself. Alright, so let's get into it. So question 1, you've got a future value table and it says a certain annuity involves making equal contributions of $25,000 into an account every 6 months for 2 years at an interest rate of 4% per annum. So we're putting in $25,000 every 6 months for 2 years at 4% per annum. Based on the information provided, what is the future value of the annuity? Okay, so first things first, you want to get your rate and your period in terms of however often you are putting money in. So in this case, 6 months. So our N, it's not going to be 2 years, it's going to be 2 years times every 6 months. So that's 2 times 2 is 4 periods. And our R is going to be 4% divided by 2 for every 6 months. So that's 2%. So I'm looking at 2%, 4 periods. So my interest factor there is 4.1216. And all I need to do is get that number. So my future value is going to be my contribution times my interest factor. So that's 25,000 times 4.1216. Pull the calculator up. So 25,000 times 4.1216. So my answer here is 103,040. That's my future value. Okay, so question 1 done. Okay, question 2. Zena opened an account to save for a new car. 6 months after opening the account, she made her first deposit of $1,200 and continued depositing $1,200 at the end of each 6-month period. Interest was paid at 3% per annum, compounded half yearly. How much was in Zena's account 2 years after first opening it? Okay, so for this type of question, first of all, you know it's an annuity because she's putting in $1,200 multiple times. Okay, but they don't give you any tables to use. So that means you need to work it out using multiple compound interest formulas. So if I just draw a diagram of what the timeline looks like in terms of her contributions. Okay, so you've got 0 and every 6-month period for 2 years. I think that's right. So basically you've got the first 6 months, 12 months, 18 months, and 24 months. Now, the detail here is she's putting $1,200 and she doesn't put the $1,200 until 6 months after she first opened the account. So in this sentence there. So I'm just going to write down, she puts 1,200 here and she puts 1,200 for each 6 months after that. Okay, now let's deal with these one at a time. So for this $1,200, this is going to get the 3% interest for 1 period, 2 periods, 3 periods. Okay, because it's every 6 months. That means this is going to be 1 plus 0.03 divided by 2, because every 6 months, to the power of, okay, it's going to be, like I said, in there for 1, 2, 3 periods. So that's going to be the power of 3. Okay, what about the second contribution? So she's putting in this for 1, 2 periods. So it's going to compound for 2 periods. Okay, so same again. It's going to be 1 plus 3% as a decimal divided by 2, but this time it's only going to be there for 2 periods. Okay, then lastly, or not lastly, second lastly, you've got this $1,200, which is going to sit there for 6 months, compounding interest. So 1 plus 0.03 over 2 to the power of 1. And then lastly, this one is not going to get any interest because she's putting in the end of that 6-month period. So it's just going to be 1,200 by itself. So what you want to do is add these all up. So let's do this. So 1,200. 1 plus So that's that first one there. So just repeat that. So plus power 2 plus power of 1. Lastly, plus the 1200. Okay, so there you have it. That will be the total. So just adding all these up, you get a total of $4,909.08. So that's how you would do that question there. Tough one, but the devil is in the detail. So just really be careful of how or when she's putting the money in. And of course, how often. Okay, let's look at the next question, 3. So here we've got a present value table. And the question asks, Fiona pays $3,000 into an annuity at the end of each of 4 years at 2% compounded annually. What is the present value of her annuity? Okay, so similar to the first question, you want to change your years and your rate so that it's in the same units as how often she's putting money in, which is annually. So actually, there's nothing really to change. So 4 years is here, 2% is there, so our interest factor is 3.8077. So present value is going to be 3,000 times 3.8077. So our answer here is $11,423.10. Okay. Now, just quickly, people get confused about whether to times or divide this number. Now, if you divided that number, you're going to get a number much smaller than 3,000, which is not going to make sense because we're trying to find out what her present value is. In other words, what sum of money could she invest today to get the same future value in 4 years' time? Okay, so that is just a quick and simple common sense check that you can use. Okay, part II. If John pays $6,000 into an annuity at the end of each 2 years at 4% per annum compounded annually, is he better off than Fiona? Okay, so let's have a look at this. So he's doing 6,000 compounded annually each year for 2 years at 4%. So let's just work this out. His present value is going to be 6,000. And what do we want? Well, we want 2 years at 4%. So that's going to be 1.8861. 1.8861. So our answer here is 11316.60. So you can see here, comparing these two numbers, that John is going to have less money than Fiona. So Fiona will be better off. By this amount. So 11423.10 minus 11316.60. So Fiona is better off by $106.05. Okay. All right, question 4. Dominic wants to save $15,000 to use as spending money when she travels overseas in 2 years' time. If she invests $3,500 at the end of every 6 months into an account earning 6% per annum, compounded half yearly, will she have enough? Okay, so once again, she's putting in $3,500 every 6 months. So we need to convert our rate into months. Okay, and obviously change however many years she's trying to get there. So 2 years is going to be, let's just write this down. So rate 4% divided by 2, because every 6 months, that's 2%. Our N is 2 years times every 6 months, which is times 2, so that's 4. So our rate's 2% and our period's 4, so our interest factor is 4.122. So our future value, right? She actually wants $15,000. So that's our future value. And we want to work out, will she have enough? So in the other scenario, we're going to have $3,500, because that's what she's depositing, times 4.122. Sorry, I crossed this bit out. She actually wants $15,000, so this is going to be a future value. $14427. So as you can see, she's going to fall short by this minus that. Okay. So no, she will not have enough. Okay. All right, next question, 5. Ralph opens an annuity account and makes contributions of $12,000 at the end of each year for 9 years. Okay. For the first 8 years, the interest rate is 4% per annum, compounded annually. And for the 9th year, the interest rate decreases 3% compounded annually. Okay, so there's 2 different parts. Use the future value of an annuity table to calculate the amount in the account immediately after the 9th contribution. Okay, so what I want you to visualize here is, for 8 years, for every year for 8 years, he's putting in $12,000. $12,000. $12,000. Eight times for 8 years. And each one of those is going to get interest along the way. So let's just deal with this 8 years first. So the 8 years, he is getting 4% compounded annually. Okay, and it's also every year, so there's nothing really to convert. So our rate's 4%, and it is for 8 periods. Our interest factor is 9.214. So I'm just dealing with the first 8 years. So his future value at 8 years is going to be 12,000, that's his contribution, times 9.214. So that's going to be 110568. Okay, so that's how much he has after 8 years. Now, it says here, for the 9th year, the interest rate decreases to 3% per annum compounded annually. So we want to know how much he's going to have immediately after the 9 years. So what we need to do is we actually need to get this number, and we just need to use the compound interest for 1 year, for the 9th year, at 3%. So let's do that. So for the 9th, so this is the 8th, 1st to 8th, and this is the 9th. It's going to be 110568, 1 plus 0.03 to the power of 1 year. So what's that equal to? So that's equal to 885.04. Now we're not done. So this is a tough question. I'm almost there, because we're not done because he makes the $12,000 at the end of each year, right? So that means we need to add on another $12,000 to this amount. So plus 12,000. So in total, immediately after his 9th year, he's going to have $125,885.04 in his account. Okay, so that's quite a difficult one, but if you break it down, it becomes much more obvious. Okay, so for the first 8 years, you have to use the table, and then for the 9th year, just use the compound interest formula. But remember to add in that extra $12,000 for the contribution at the end of 9 years. Okay, question 6. So once again, we've got a future value table here. Zal is saving for a trip and estimates he will need $15,000. He opens his account earning 3% per annum compounded annually. How much does Zal need to deposit every year if he wishes to have enough money for the trip in 4 years' time? Okay, so what this guy's trying to get is, he's trying to get $15,000 at the end of 4 years, and we want to work out how much money he needs to put in. So we're actually got to work out what his contribution is going to be. So we got to work backwards. So first of all, let's just change these rates if we have to. So he's putting money in every year, it looks like. Every year. So there's not going to be any changing. It's 3% per annum, and it's in 4 years. So let's highlight that, 3% and 4 years. So his interest factor is 4.184. Now, usually it's future value equals contribution times interest factor, but we know his future value because we want 15,000. And we want to work out the contribution. So it's going to be times his interest factor, 4.184. So therefore his contribution is 15,000 divided by 4.184. So his contribution is $3,585.09 per year, just to make it obvious. Okay, now before I move on, some math teachers might grill me about this, but you don't really need to understand what this is talking about. Okay, because so as long as you know, once you get your interest factor, which is not very hard to do, there's only two options. You either times or divide this 15,000, really. Okay, now if you divide it like we have, you get a number which makes sense in the scheme of things. So he's going to deposit $3,585 every year in order to get 15 grand. Okay, but if you multiply 15,000 times the interest factor, you get 62,760. It doesn't make sense. He's not going to deposit 62 grand every year in order to get $15,000 at the end of 4 years. Why not just pay it up at the start? Okay, so that's a little common sense trick that you can use. One more thing is, if they give you a table like this, the future value table, make sure you use it, okay? All right, here we go, part B. How much interest will Zal earn on his investment over 4 years? Give your answer correct to the nearest dollar. Okay. Much easier than it seems. So don't get it twisted. Just think he's depositing this much every year for 4 years. So how much money has he put in over 4 years? So 3,585.09 times 4. $3,585.09 times 4. So he's only put in $14,340.36. But in the end, as we figured out at the start, he gets $15,000. That must mean the difference is going to be the interest. So therefore, the interest is 15,000 minus 14,340.36. $659.64. Okay, or to the nearest dollar is $6.60. Okay, cool. Let's go on to the next one. Okay, 7. Josephine invests 50 grand for 15 years at an interest rate of 6% per annum compounded annually. Okay. Emma invests $500 at the end of each month for 15 years at an interest rate of 6% compounded monthly. Financial gain is defined as the difference between the final value of an investment and the total contribution. So in other words, what's the interest? Who will have better financial gain after 15 years? Use the table below to justify your answer. Okay, so let's break this down. Now, before I even start, I know I'm going to compare two people. So I've got Josephine and Emma. Now, I like drawing tables to simplify things. Okay, now let's look at Josephine. She invests 50 grand for 15 years at an interest rate of 6% compounded annually. Now, she's investing 50 grand just once. So that must mean it is the compound interest formula. So you're going to have FV equals PV, 50k, 1 plus 0.06 times 15. So in 15 years' time, she's going to have 119,827.91. Right, so it's pretty good on her part. Okay, let's do Emma. Okay, so Emma invests $500 at the end of each month for 15 years at an interest rate of 6% compounded monthly. So you know for this one, you need to use a table because she's contributing $500 at regular intervals. So let's figure out her interest factor. So it's 6% compounded monthly. 6% per annum compounded monthly. So that's 6% divided by 12. So that's going to be 0.5%. And her N is 15 years times every month. So that is 12. 15 times 12 is 180. So look for my rate. So it's 0.5% and 180. So 290.8187. All right, so here we go. Her future value is going to be her contribution, which is $500 times her interest factor, which is 290.8187. Whoa, 290.8187. So she's going to have $145,409.35. All right, now we need to address this line here where it says, and I'll maybe do a different color. It says financial gain is defined as the difference between the final value of an investment and the total contribution. So we need to work out for each of them individually how much interest they've earned, I guess. So if we just look at Josephine to start off with. So how much interest has Josephine made? So she invested 50 grand and in the end she got 119,000. So her interest is going to be the difference minus 50,000. $69,827. So that's for Josephine. Now we got to work out Emma. Okay, now Emma's a little bit more complicated, right? Because she has invested $500 for 15 years every month. So her interest is going to be 145, so her future value. And we need to take away all her contributions. So that's $500 each month for 15 years. Mistake there. So her interest is 55,409.35. So here you can see who has better financial gain. Well, it looks as though Josephine has more money in the end, so therefore Josephine wins Okay, that's a tough question. A lot of little details. I would advise you to break it up into a table and really read carefully. Because I reckon a lot of people would stop here and go, okay, so Emma's better off because it looks like she's got more money in the end. And that's where they trick you. Because Emma's actually put more money in order to get more money at the end. But her actual interest is smaller than Josephine's. All right, question 8. The table gives present value interest factors of an annuity of $1. So we've got present value table here. Oscar plans to invest $200 each month for 74 months. His investment will earn interest at the rate of 0.08 as a decimal per month. Okay, so use the information in the table to calculate the present value of his annuity. So $200 every month for 74 months, and the interest rate is 0.008 per month. Now notice I said month 3 times, so there is no conversion. So his interest rate is this. As I state, his R is 74, so its interest factor is that number there. Okay, so let's pop that in. So his present value is going to be his contribution times his interest factor, 5568446. So it's $11136.89. Okay, so that is his present value. Okay, so I just want to make it a quick comment. Present value table, future value table, completely separate. So don't get it twisted. Okay. If you want to know more about present value tables, or you want to know more of what the present value actually means, I've got a video on that, so check that out. But if you just want to know how to do the calculations, I think knowing this is enough. Okay. So part II, Lucy is using the same table to calculate loan repayments on her car. Her loan is $21,500 and will be repaid equal monthly repayments over 6 years. Her interest rate on the loan is 10.8% per annum. Calculate the amount of each monthly repayment correct to the nearest dollar. Okay, so we've got to do some conversions here. So N, she is doing 6 years every month, so that's 72 months. Her rate is 10.8% per year, and we need to divide that by 12. That's 0.9%. And we want to have $21,500, okay? So to work this out, it's going to be 21,500 divided by her interest factor. So let's get that. 72 at 0.9%, which is going to be 0.0090. Okay, so that's divided by 52.82118. So she needs to contribute $407. So she needs to contribute $407 to the nearest cent. All right. Cool. So once again, this is one of those situations where just common sense it. You're going to have to times or divide your interest factor. If you don't divide in this II case, it's going to be way bigger, okay, than 21,500, and it's not going to make sense. Okay, question 9. Here we've got another future value table, it looks like. Margaret needs to save $75,000 over 6 years for a deposit on a new apartment. She makes regular quarterly contributions to an investment that pays 3% per annum. How much will Margaret need to contribute each quarter to reach her savings goal? Okay, so hopefully by now you're seeing a pattern of what to do. We've got a future value table, we've got an amount that she needs to get to, and we've got her rate and her years that you either have to convert or you don't. So she's 6 years and she's doing this every quarter. Okay, so and also 3% every quarter. So let's work out your rate. So it's 3% divided by 4, because every quarter, 0.75%, and an n, right? So n is equal to 6 years. So you need to times that by 4, because every quarter, so that's 24 periods. So in 24 and 0.75 is 0.0382. Okay, so she needs to have 75,000. So we need to times this. So future value is equal to 75,000 times by 0.0382. So that's going to be equal to 2865 per quarter. Okay. Now, I kind of brushed over this, but for those of you who want to know why I actually times and didn't divide, which is what we've been doing before, is this keyword here, contribution per period. Okay, of an annuity of $1. So it's actually saying to you that this table is calculating the contribution. Okay, but once again, just common sense check it. So had I gone divide, I get some astronomical number, which is just not going to make sense for her to contribute each quarter. Okay, so that's why I kind of brushed over it. It's obviously better if you don't, but I just want to stress that these questions get very similar over time. And if you do enough of them, you realize, okay, there's only two ways you can go, either times or divide. Question 10. The table shows the future value of annuity $1. Once again, so now it's just future value, no contribution. The annuity account is opened and contributes $2,000 at the end of each year for 7 years. For the first 6 years, the interest rate is 4% compound annually. For the 7th year, the interest rate increases to 5% compound annually. Calculate the amount immediately after the 7th contribution is made. Okay, so this is almost exactly the same as a question we did towards the start of this video, where you just want to break it down. Okay, so the first 6 years, I'll just go, maybe I'll write year 1 to year 6. She is doing $2,000 each year for 6 years, compounding annually. So that's going to be 6 years at 4%, so our interest factor is 6.633. So future value is 2,000 times 6.633. So at the end of 6 years, she's going to have $13,266. Now, year 7, make this pop a bit. Year 7, her rate actually increases to 5% compound annually. So we're just going to have to do a compound interest formula here. So future value is 13,266, 1 plus 0.05 to the power of 1. Can obviously leave the 1 out, but I'm just leaving it there to show you. So in the 7th year, she's got this, 13,929.3. But like the question before, this is the detail you need. Contributions are made $2,000 at the end of each year for 7 years. So you actually have to add on another $2,000 for the end of the 7th year. So I think that is going to be 15,929.30. Okay, that is done. Okay, question 11. So we've got a present value table. It's just a regular one. A bank lends Martina $500,000 to purchase a home. Interest charge at 1.5% per annum compounded monthly. She agrees to pay the loan by making monthly repayments over a period of 30 years. How much should the monthly repayment be in order to pay off the 30-year loan? Okay, so almost the same processes, well, pretty much the same process we've been going. Our rate is 1.5% divided by 12 because it's per year and we're compounding monthly, or she's making monthly repayments. So that's 1.5 divided by 12, and then divide by 100 to get a decimal. 0.00125. Our N is going to be 12 months times 30 years. That's 360, yeah. So there it is. Now we just got to work out the monthly repayment. So monthly repay is going to be 500,000 divided by the interest factor, which is 289.754111. So her monthly repayment is 1725.60. Okay, sweet. That's quite straightforward. So hopefully you are actually getting the gist of what to do here. They're very, very similar once you smash out enough questions. Okay, question 12. So we've got a future value table, and the question says, Simone deposits $1,000 into a savings account at the end of each year for 8 years. The interest rate is, for the 8 years, is 0.5% per annum, compounded annually. After the 8 deposits, Simone stops making deposits but leaves the money in the savings account. The money in the savings account earns interest at 1.25% compounded annually for a further 2 years. Find the amount of money in Simone's saving account after 10 years. Okay, so super similar to the question we did 2 questions ago. So for the first 8 years, so year 1 to year 8, she's doing $1,000 each year for 8 years, compounded annually. So 0.75 per annum, nothing to change, 8 periods. So that's going to be times by 8.2132. So that's just $8,213.20. Now, it says after the 8th deposit, Simone stops making deposits, but leaves the money in there for another 2 years at 1.25% compounded annually. So easy, right? So year 8 to year 10 is just compound interest. So future value equals 8213.20, 1 plus 0.0125 for 2 years. So her future value is 8,419.81. Okay, done. Okay, last one. Wilma deposits a lump sum into a bank which earns 2% per annum compound interest. Here we've got a present value table. Okay, so here's a scenario. Wilma is able to make the following withdrawals from this account. So $1,000 at the end of each year for 20 years, starting 1 year after the account is open, and $3,000 each year for 10 years, starting 21 years after the account is open. Calculate the minimum lump sum Wilma will have to deposit when she opens the new account. Okay, so here we're trying to work out basically what she needs to put in order to be able to take this money out. Okay, so first things first, let's deal with this one. So she wants to have $1,000 each year for 20 years. Okay, so let's deal with that. And it's all going to be 2% compound interest, 2% per annum. So in this first scenario, let's just call this scenario 1. Okay, pencil's dead. We'll be back. All right, we're back. So pencil's charged, and let's go back to this situation. So we've got the first scenario, which is where she withdraws $1,000 each year for 20 years, for the first 20 years. And then scenario 2, where she withdraws $3,000 each year for 10 years, but importantly, it's from the so it's starting from the 21st year, so from the 20th year to the 30th year. Sounds confusing, but let's just deal with scenario 1 first. So scenario 1, she's withdrawing $1,000 each year at 2%, so 0.02 for the first 10 years. So that is, oh sorry, for first 20 years. So 16.351. So let's work that out. So 1,000 times 16.351. Could have done that in my head. Okay, so that's scenario 1, that she needs to, well, I don't want to confuse you, but that's the amount of money that she needs to put in as a lump sum in order to withdraw $1,000 for 20 years. Okay, now scenario 2 is a little bit more tricky because, just draw a quick timeline for you. So this is it's a starting 21 years after the account is open. So that's going to be, because she's making withdrawals at the end of each year, that's going to be at the end of the 20th year, where she starts getting $3,000, and obviously to the 30th year. So we need to work out what the difference is in terms of the 30th year and the 20th year, because she's actually withdrawing more money during that period. So let's just take the 30th year to start off with. So 3,000 times 22.396. That's 67188. Now we want to work out the 20th year so we can find the difference in terms of the lump sum that she would have had to put in order to get the extra $3,000 each year from the 20th to the 30th year. So 3,000 times the interest factor. Now it looks like it's the same from scenario 1. So it's from the 20th, so 16.351. So that is 49,053. So the difference, so the lump sum of scenario 2 is going to be the difference of scenario 2, 67,188 minus 49,053. So that's 18,135. So therefore the total is going to be this plus the 16,351 that we had before. So scenario 1 plus scenario 2 is $34,448.60. Okay, so that's a real tough one because you need to understand that the change, okay, so the change from the 20th year to the 30th year is what is hard, because you need to treat it as though they're separate annuities. So for scenario 1, that's pretty straightforward, so because you're just doing the first 20 years. But because you're trying to break up the 20th to the 30th year, you've got to work out the 30th year and take away the 20th year. Otherwise, it's going to be out of whack. All right, so I hope this video helped. If you've got any comments or I've made any mistakes, definitely let me know. But if you like these type of videos, also let me know. I can definitely do more of them. Thanks for watching. I'll see you in the next one. Peace.